Hello everyone, I'm John Paparrizos. I'm a postdoc at the University of Chicago and I will present VergeDB. I believe the importance of managing IoT data is well understood, considering how IoT applications have revolutionized entire industries. However, in order to meet the scaling demands of IoT applications, I believe new systems are necessary to be designed. To understand why this is the case, IoT solutions that rely on traditional database systems, they can no longer keep up with the scaling demands of these applications. In many cases, we have to ingest millions of numeric data, and these systems are not optimized for this type of workloads. As a result, we have seen a rise of new database systems that are showing much better performance because they're treating time series as first-class primitives. Currently, in the scientific literature, as well as in industrial settings, we're observing two main trends. From one side, we are having systems that are completely agnostic to the task that has to be solved. These systems, they mainly support SQL-like operations for filtering and aggregation. On the other side, we are having systems that are specialized for particular applications. For example, we want to perform anomaly detection on smart meter devices. Currently, we are not aware of systems that live in between those two cases. So systems that are of general purpose, capable to optimize their performance by being aware of what task has to be solved. So IoT devices, they sense their environment, they collect data, and they push this data in a more centralized location for subsequent storage and analysis. By centralized location, we mean some cloud service or some data center in between the cloud and the edge devices, as is in the cases of fog computing and edge computing. However, in modern IoT applications, we are having new requirements for processing, which poses new challenges. To go through some examples, there is clear need, for example, to support real-time decision making. Consider drones and autonomous vehicles that they have to avoid obstacles. So there is no space here for dashboards and humans performing analytics and then triggering additional actions. In many applications, we are having very low latency requirements. In other cases, we have to analyze sensitive or private data that they cannot be moved outside of these edge devices, or we don't have the appropriate bandwidth to make such move of the data to a centralized location. Even if we have the available resources, in most of the cases, this is completely unnecessary and actually is becoming very costly. So we're seeing a clear demand for pushing a significant portion of the data computation in the edge devices. So to achieve that, compression plays a very important role. And this is for two reasons. First of all, by reducing the size of the data, we're immediately achieving much better results in terms of how much information we have to compute, which reduces the power and the bandwidth utilization. However, with careful design of compression mechanisms, we're able to perform queries directly on the encoded data, which maximizes the performance. And this is very important when we have to deal with limited resources in terms of in these devices. We need to take into consideration that we are having a transition between SQL type of analytics to much more machine learning based workloads. Tasks that often have to be performed on IoT settings is anomaly detection, pattern recognition, clustering classification, and so on and so forth. In addition, we have to meet several requirements about heterogeneous resources. For example, we have devices that are of very low resources, such as embedded devices, but we're also having mobile devices and wearables that are essentially small computers. Even though compression and selection of compression mechanisms for in the database context, they have been very well studied in the past, currently we believe that there is very limited attention on how these methodologies, they can affect the downstream performance of the IoT tasks. So we believe that there is a great opportunity for IoT data management settings to make appropriate selections of compression mechanisms that are conscious to the task that has to be solved. For this reason, we have been developing VergeDB, which is a system to enable analytics on edge devices. How it differs from current IoT solutions, first of all, it adapts to the available resources, and it also does that by making appropriate selection of compression methodologies that are relevant to the tasks that has to be solved. To do this, we have to treat machine learning and complex analytics as first-class operations. So VergeDB has to perform needs several modules in order to achieve this goal. For example, we need to be aware of the available resources so that we can maintain, so that we can properly allocate them and maintain particular characteristics. Like, for example, particular ingestion rates that are needed in these IoT settings. We're having modules that are taking care of what compression mechanisms are required, and if access to the original data are also needed to answer particular queries. Once such decisions are taken, the compression manager will take these compression methodologies and apply them to the available data to solve particular tasks. And of course, when no resources are available, we need to take decisions on pushing the data to a more persistent storage and eventually to the cloud. Considering the time constraint, I will focus more on the compression manager. Currently, the VergeDB is supporting three main compression methodologies. We're having support for byte-oriented compression. We're having support for lightweight encodings for numeric data, as well as specialized time series representations. What is the issue with this approach is that some of them, they require to be decompressed before, they require to decompress the data before any analytics run on top of this data, or in other cases, the data are summarized in such a way that is not useful to be used for the downstream task. As a result, we have been exploring new compression schemes, but we believe they cover a large range of settings and operations that are necessary for IoT applications. For example, we are having compression schemes that are preserving the similarities between time series, which is very useful for machine learning tasks. In cases that we know that the values of the particular application are bounded to some particular range, we are able to achieve much better performance by utilizing such information. Or we are also developing sampling methodologies that are much better capturing the temporal characteristics. I will give some high-level overview of the similarity preserving compression schemes, and you can find more details for the rest of the methodologies in the paper. So currently, the time series representations, they are not capable to support similarities between pairs of time series. And why this is happening? Because when we are designing methodologies for analytics in time series, we need to take decisions about how we should compare the data, how we should represent the time series, and how we should organize this data in order to enable indexing and fast processing. Unfortunately, all of these components have been developed independently from each other, and as a result, they're incompatible at this point. So we're having state-of-the-art approaches for comparing time series that are incompatible to the representation methods that currently exist. So what we have been exploring is approaches to let us learn how to compress the data while preserving similarity functions provided by the user. And we have already published some material on that on VergeDB in 2019. You can find more details there. In high level, what you have to do is essentially to extract a dictionary that lets you use this as a reference point between the historic data and the new points that are arriving in the system. You have to estimate the necessary parameters to achieve particular accuracy goals, and then solve an optimization problem that lets you learn these compact representations that you are able to use to perform queries without the need to decompress the original, without need any decompression. In the context of VergeDB, we have been exploring some variants of this methodology in order to subsequently quantize these learned representations, such that during querying time, we only have to visit a very small portion of the search space. And we have seen that we are not only more accurate than existing methodologies because we support much more advanced distance measures, but they are also capable to achieve similar runtime performance. In addition to that, we have seen that our system is capable to achieve close to 2 million points per second ingestion rates when various compression methodologies are being used, which is very helpful for this type of IoT settings. With that, I will finish my talk, and I'm happy to take any questions.